Hello, I'm Jae-hyung Jung from Seoul National University, Republic of Korea, and the first author of the paper titled Photometric Visual-Inertial Navigation with Uncertainty-Aware Ensembles that was published in Transactions on Robotics. This was done by me, Dr. Young-gun Choi, and my advisor, Professor Chan-Kook Park. The first motivation of this work is to deal with low-textured scenes. Most of the previous visual inertial navigation systems, VINs, adheres to repeatable or salient visual features. Therefore, estimation accuracy would be degraded in low-textured environments. An example is shown where VINs fusion and robust VIO do not track many features on the low-textured floor. Inspired by the famous direct sparsometry, we directly minimize the intensity difference, also known as photometric error, formulated in iterated extended Kalman filter fully embedded on matrix Lie group. Our method can utilize features in a low-textured environment if they have locally distinctive gradients, as in the left example. But the photometric error is highly non-convex due to nonlinearity in image intensity. In other words, it is very sensitive to an initial point. To solve this, we introduce an optimal image gradient that minimizes linearization error within the projective uncertainty. In this black and white toy example, the conventional gradient only at the mean represents 0 or plus minus 1 gradient. However, if we have knowledge about projection uncertainty, for instance these green ensembles, we can answer more reasonably about the image gradient. This leads to higher robustness to bad initialization. In this illustrative example of virtual parking lot in AirSim, let me close up a lane on the ground. The goal of this example is to minimize the photometric error of lane edges between temporally consecutive, that is, reference and current images. As claimed in the previous slide, the conventional gradient is trapped in badly initialized points due to weak image gradients. Therefore, the filter state, that is pose and structure, is converged to the wrong state. We minimize the expectation of the linearization error squared in the image domain to obtain the stochastic image gradient, h hat. In the same scenario, but with stochastic image gradient, the proposed image gradient pulls the pixel position to the correct direction in the minimization problem. Since it is not straightforward to analytically implement the stochastic gradient, we sample ensembles according to the state uncertainty in the image domain. We further investigate the actual value of image gradients during iterations. Each ensemble contributes to the stochastic gradient that minimizes the linearization error. Thus, we term our method as Ensemble Visual Inertial Odometry, NVO. We open source our NVO in GitHub repository and feel free to check for more details. To validate the effectiveness of the stochastic gradient, we run 50 times Monte Carlo simulation with large initial velocity uncertainty, that is standard deviation of 1 meter per second. This shows velocity estimates along with the true value of iterated EKF with and without stochastic gradient and with different image parameter levels. This confirms that the stochastic gradient, colored in red, shows nice convergence behavior yielding the most accurate and consistent estimation results. Let me highlight the parking lot sequence in AirSim. As a representative single realization in the Monte Carlo simulation, the conventional gradient fails to track features due to intensity nonlinearity, while in NVO, features are successfully tracked using uncertainty-aware ensembles. To compare NVO to state-of-the-art VINs, we recorded stereo images, IMU readings, and 6 degrees of freedom ground truth posed by a motion capture system. The most of scenes are full of low-textured flower that is very challenging for VINs. NVO uses locally high gradient features on the floor to minimize the photometric error, while Vince Fusion does not track enough stereo features due to lack of textures. It can be interpreted that this leads to less position drift in NVO. This time, a drone was in autopilot, flying a rectangular trajectory. Again, NVO uses locally distinctive features on the floor, while robust VIO tries to select high-scored fast corners that are mostly concentrated on windows. We can say that this feature selection strategy leads to moderate drift in NVO, but a large position drift in robust VIO. We recap test results by summarizing pose error and computation time on modern CPU. In this total of 4 flights, where most of scenes are captured in a low-textured environment, NVIDIA achieves the most efficient localization in terms of estimation error and computing time. NVIDIA included around 200 features and shows the real-time feasibility at most 27 frames per second. And in our laptop CPU. Also, NVIDIA outputs valid covariance estimates as errors are contained in the 3 sigma bounds. Thanks for your attention and feel free to ask questions and check our NVIDIA in GitHub.